Okay, everyone, welcome back. Let's continue to talk about electricity and magnetism calculus treatment. This time, let's talk about current and resistance, macroscopic and microscopic properties. We are going to deal with, again, practice physics, calculus-based treatment of electricity and magnetism. We are going to stay with the Katz book, first edition, and look at some problems from there. Chapter 28, problems from Chapter 28 associated with pages 890 to 894. All of these problems that are down here, the solutions to them will scroll at the end of the video. I will try to do these 8 problems, perhaps over 2 videos. Problem 20, 33, 34, 76, 77, 80, 81, 82. But all of these problems will scroll at the end of the film. The solutions to those problems, better said. So that's understood. Frequently look at the end of the video and you see the solutions to the problems, how they looked in PDF format, basically, just scrolling at the end of the discussion. Well, that's the goal. Let's see what we can do. There are a few things I've put up on the board here. I put a conductor, I put a cross-section. I'm showing a cross-section of a conductor we are assuming positively charged particles flowing. Usually it is the negatively charged particles, the electrons, about which the real, the direction of the charges, the charges. If there's an E field going in that direction, positively charged particles will go in that direction toward your right. If there are negatively charged particles present with that same E field going to the right, the negatively charged particles will go to the left. It's really the only difference. All the other properties hold up. They always work under the assumption that we're dealing with, not always deal with that assumption, but frequently like to deal with the assumption that we're dealing with positive charge carriers. The flow of current is the flow of oftentimes imaginary positively charged particles, how they behave. The negatively charged particles called electrons behave in the exact same way, but just go in the opposite direction from that. So that's the convention. So we'll say that there are positive charge carriers present in this wire, and we're taking a cross section, the red, from red cross section to the other red cross section, what's going on? From area 1 to area 2, can we say a few things? Can we draw some conclusions? And the conclusions that we draw end up going over here. We end up saying, well, there's this thing called charge density. And it's a vector, but for our purposes, let's look at it as a magnitude right now. The charge density J is the amount of current passing through a particular cross section. The amount of charge passing through a particular cross section per unit time. That's Q over T, or dQ dt. So it's the current divided by the cross sectional area. That is the current density. The current density is current divided by area. The current density is directly proportional to the E field. You need an E field to, E field, many things are accomplished within the context of an E field, and when you're in the presence of an E field and things are moving, charges are moving, you need to put a particular amount of work in to overcome a particular E field if you're going to go to higher potential. If you're going to go to lower potential, there's a particular amount of potential energy that is being released, so to speak. So it would make sense, I guess you could say, that the greater the electric field, the greater the electric field vector, the greater the current density vector. We are going to end up showing that the current density is going to be the charge density per unit volume, the amount of charges per unit volume that are moving, the charges, the charge per carrier, they call it E, which is 1.6 times 10 to the negative 19th coulombs. That is the charge E, and this is the number of charges that are present in a given unit volume. So N is the charge density per unit volume. This is the charge per charge carrier, and V sub D vector is the drift velocity, the per carrier. Roughly speaking, on average, how fast is each carrier moving in the direction of the E field for you to have a charge density J vector. We're going to show that V sub D is, well, it's, the negative here just means if you were dealing with a there's, for right now, don't even worry about the negative. They've got it in the book, and it's almost better off you don't even have it there. For our purposes, in the absence of all other forces, there's a charge times an E field. A charge times an E field is a force. A force divided by the mass of the charge carrier, in this case an electron, or you could say an imaginary positively charged electron, or negative. Here they got it as negative, so let's leave it as negative. And it is negative, obviously, but I'm saying right now we care about the magnitude. That's the real big thing that is being said right now regarding this. So what's going on here? Well, charge times E field is force. Force divided by mass is acceleration. Acceleration, starting from 0 for a particular amount of time between collisions, will give you the final velocity attained, or at least it'll give you a big portion of it'll give you the velocity and some sense of what kind of velocity is attained between collisions. Okay, we can argue this a whole bunch of ways, guys, but for our purposes, they're going in this direction, let's us go in that direction as well. That would be V sub D. Well, the charge density, we said, is directly proportional to the E field. And a lot that goes on here, you guys. So let me try to exactly see what we could say here. So forgive me, the current density directly proportional to the E field. Okay, we got that straight. If V sub D vector is equal to, as we said, don't worry about the negative right now as much, and there's some other subtleties as well. For our purposes, what's V sub D vector in a ballpark idea of what's going on here? Per charge carrier, some more, some less. Let's see what's going on here. Well, charge times E field is force. Force divided by mass is acceleration. Acceleration times time will give you the velocity that's attained. Some sort of mean, some sort of time between collisions between other charge carriers. While it's not colliding, it's gaining speed, it gains a particular speed, gains a particular velocity. You got this. Well, I'll tell you what, why don't you put, for V sub D vector, put all this in here, but use the positive portion. We want a magnitude here, and put that right here for V sub D vector. Well, then it becomes NE times E big E over M sub E TMF. Well, that's where we get this. And again, it's directly proportional. The current density and the E field are directly proportional to one another. The current density is directly proportional to the E field that's being applied, and we got this right here. Well, that's interesting. If this is a big number for a given E field, then it's going to give you more charge, more current density, more charges flowing past, or effectively more charges flowing past a particular cross-sectional area per unit time. Current density is going to be bigger if the E field remains unchanged, but this is a bigger number. Well, this right here, they call it sigma for conductivity. Sigma, the conductivity, is equal to this right here, and if this is a big number, it is indicative of a large current density for a given E field. Great. J vector equals sigma E vector. They got this thing called resistivity, which is the inverse of conductivity. Rho for resistivity is 1 over sigma. Well, if that's the case, if you wanted to solve for E vector, you could divide by sigma on each side. E vector would be 1 over sigma times J vector. 1 over sigma is the resistivity. So if there's a lot of resistivity, to the flow of current, there's a lot of like fight. The material just doesn't want to conduct electricity that well. If there's a lot of resistivity, if rho is a big number and J vector is still a big number, despite the fact that rho is a big number, because rho's fighting it. If rho and J vector are really big, when you multiply them together, you've got to have a huge E field for there to be a lot of J vector in the face of a lot of resistivity. So that's some of what they're talking about. Now, this is going to make sense when we can get it to here, then everything else everything I said follow. This is the big thing right here. If we can get it to here, guys, talk about this, we can derive all the other stuff. Now, this right here, they made the analogy in Dr. Katz's book, brilliant analogy. They said it was G vector. It was an analogy of G vector times T to get a particular velocity. Well, how much is this thing attaining before it hits something? Now we could talk about average velocity and a lot of other stuff. There's probably a lot more subtlety to this than I'm sure there's a lot more subtlety to this than we're discussing at this point. But this at least gives us a gut feeling that, look, if there's very much time, relatively speaking, between collisions, they tell us it's a good conductor. If there's not very much time at all, then you're talking more, it has more resistive qualities than conductive qualities compared to this one, where it's like if T is a real big number, that means there's a lot more freedom for the charges to flow, because this is the amount of time that it takes for a collision to take place. The time between collisions, okay, or it's associated with that very strongly. Okay. Dr. Katz's book handles it very well on page 871, and it's pretty brief, goes pretty well. And once we've got that, I think it opens the door for everything else that we're doing. So this is kind of a drawing verbatim from Dr. Katz's book regarding what's proved on page 871 regarding a lot of this stuff. Once you've got this, you guys, everything else is believable and follows. Okay, just to see exactly what they were doing here, they were saying, they're talking about the mean free time. The average time between collisions is called the mean free time. So that's basically where the MF comes from. Time, mean free time. Okay. Let's see how that works out. And like I said, once we've gotten this derived, all of these are believable from what we've already said. Some of these are already believable before we even derive this. We can say, to a large extent, this, very believable, as is this. Can you just get a little more of the specifics right here, and then to be able to call that sigma right there? Okay. Well, that we already did right here, and we said, okay, V sub D we solved for V sub D using this, and everything here was more or less constant for a particular situation, and it depends on the material to a large degree. If this is a big number, for a given E field, you've got a lot of current density. If this is a small number, for a given E field, you have a small current density. And that's where this was all playing into it. So let's get that to work. Let's get that to be true. We'll be surprised some of the numbers that they get when we actually plug in numbers to something like this. But let's look at it and see what we can say. So this is what we talked about. Here's some goals here. I'm going to try to hit these 8. It may, we'll see if I can do it. How we're going to do it. I may have to take a break with it and come back with it, but we should be able to put it in one video for everyone, in one film. So we'll cross every bridge as we need to cross it at that point. Well, what's going on here? There's a flow of these imaginary positive charges. So there's an E field also pushing. All of these are like positive test charges, and if there's an E field going to the right, positive test charge and or charges will also go to the right. So the E field goes to the right and the positive test charges go to the right. They go to the right with a speed, magnitude V sub D vector, or V sub D vector, we'll say is generally what's happening right here. How far do they go in a differential amount of time, dt? Well, V vector, V sub D vector dt will give you dx vector, and we can kind of take it from there. Well, Dr. Katz puts it pretty well. I mean, we're going to try to show this. We're saying, okay, the particles tend to flow in a particular manner. The amount of charge passing through one in the time, area 1 in the time interval dt depends on the number of particles n passing through and the amount of charge E that each one carries. So the amount of charge dq, so they say a lot, they play this a bunch of ways, I guess you could say. The amount of charge that will pass through 1 right here, and it'll eventually pass through 2, but let's see what happens between them. That could be of great interest as well. But the amount of charge that passes through, the amount of charge, so first things first. I mean, they gave this to us, so we know this is of importance to do that. Dx vector equals V sub D vector dt. V sub D vector, based on what we know about calculus, we're getting this. So we know that. We know how that all plays out. The amount of charge dq passing through area 1, in the time interval dt depends on the number of particles, capital N, the amount of charge. The amount of charge dq passing through 1 in the time interval dt depends on the number of particles, capital N, going through there, and the amount of charge E that each one carries. What's going on here? Well, the amount of charge that's going to pass through here in any particular interval of time, there's going to be about, the dq amount, that it's going to depend on the total number of charge carriers that get through there. True. Total number of charge carriers that get through there in a differential amount of time times the charge that's on each one. So you can kind of look at it like that. Now, if that's the case, it's in a differential amount of time, you guys. So it's dq equals ne. E is just, let's not get caught up with a positive and negative. E, a negative right up here, just means the charge on an electron. We're going to assume positively charged particles, given the convention of how they speak about matters like this. The charge here is the magnitude of the charge that's on an electron, which is 1.6 times 10 to the negative 19 coulombs. This right here, just by itself, the E is 1.6 times 10 to the negative 19 coulombs, and capital N is the number of charge carriers, each one carrying that amount of charge, passing through number 1. And that's the dq. That's the dq that they're talking about. We find capital N from, here's some interesting stuff here. We find capital N from the number density of the actual conduction electrons. Most conductors have 1 conduction electron per atom. So the number density of the imaginary particles is equal to the number density, small n, of atoms in the metal, and capital N is the number density of the particles, and capital N is the number density of the particles n times dV of that proportion of wire. Basically, guys, if you want, for anything, let me just say this really quickly, erase it, and then go more in the differential form. If you want to know the total amount of particles that are present, this is the number density, the number of particles per unit volume, times the volume, and that'll give you the flat out, that'll give you the end of it right there. So to stay faithful with the differential forms that are talked about here, what does that mean? Well, n, and n can still be a huge number, even though they're, what you're talking about here. If you want to find what n is, capital N, it is the number of charge carriers per unit volume times a differential amount of volume will tell you the flat out number of charge carriers, period. This is a constant for a particular material. Multiply it's a number of charge carriers per unit volume times a particular amount of volume. Bam, it'll tell you the raw number of charge carriers. Each one of those charge carriers, each one of those N charge carriers, capital N charge carriers, has a charge associated with it of this much. So if you multiply these two, you get the total charge that's actually going on. Don't let the DQs and DVs kind of throw you off. It still works just fine. The volume of the orange portion of the wire is its cross-sectional area A times the length of that portion dx. So you could say a lot of stuff here. I mean, this is a pretty big cross. It looks pretty big. I don't want to. So you could kind of say, okay, what is all this in here? I hope I don't regret drawing it like this. Okay, all this stuff that's in here, I don't want to copy right over it, but this is, what's that volume all about? Well, that volume is the delta V. The delta V is the cross-sectional area A, which is here. Capital A is the cross-sectional area here, and it's also capital A, the cross-sectional area here, and also capital A, the cross-sectional area there, for our purposes. So what's going on here? Well, they're saying that the delta V, this seemingly huge thing, we've just kind of blown it up and just looking at a small portion of it, that's delta V. Well, what is it? Well, what is delta V? It's the cross-sectional area times the length of the cross-sectional area. So you're doing that. Absolutely true. So what else do you want to say about that? Well, we could say a lot of things about that. We haven't really quite said it, but we'll say, lose the vectors for a minute and just say this. dx is v sub d. And how did they write that? Tell me it's not. Okay, did I write capital? I shouldn't have put capital. It's the same thing, guys. So it's lowercase. Not a big deal. Okay, that's just so let's write it like this. There's more subtlety to all this than I think initially meets the eye. But for our purposes, we're good. We're fine. We're very fine. dx equals v sub d times dt. So what does that mean? Well, dx equals v sub d times dt. Yeah, absolutely. I mean, we know that. I mean, we from this, the mathematics was already pointing in that direction. Dx vector equals v sub d vector times dt. V sub d vector equals dx vector dt, et cetera, et cetera. See what we can say here, guys. So we got it down to there. Find the number of particles that pass through cross-section 1 in the time interval dt by substituting, and they talk about certain things here. So let's see what we can say here. The number of particles that are going to be there. Well, the number of particles are right here that pass through this cross-section. Now look, guys. These particles, how are they going to pass over? How are they going to come over there? There's going to be, we're assuming more or less a constant speed, a constant flow rate. So whatever this volume is associated with a length and a constant area, there's the same length associated with constant area right here. So if all that's here passes through here, and there's a volume dV of the amount that passed through here, there's a volume dV that'll pass through here, and a volume dV that'll pass through there, and so on and so forth. These are moving. And it's the same amount of volume as you go, wherever you go. If this were 100 miles long, at mile 1, some place, some cross-section, it's the same situation, let's say, for our purposes. However, let's say it's a real long wire, 100 miles, maybe it's an extreme situation here, but wherever you are, in terms, for the purposes of the discussion here, wherever you go on this very long wire, when you take the cross-sectional areas, and you look at a distance between the two cross-sectional areas, distance times cross-sectional area is a volume. Whatever amount of charges are there that end up leaving that location and go somewhere else, that same amount of charges will also leave the new place in the same amount of time, and so on and so forth. So the way they're looking at it, the way you can look at it is, what are you going to say about it? Well, I mean, we've said a lot already. We've said this. The delta V is this. Sounds good to me. Here's the number density. Here's, why am I calling it delta V, guys? dV. That's the, dV is the calculus analogy to the, is the continuous, dV is the continuous analogy to the discrete analogy of delta. Okay. dV is all this, dV is this, dV is that. Let's talk. Yeah, the dt assures you of the differential character, that it continues as you're deriving this. Yeah, sounds good to me. We already said that the dq would be everybody times the charge E. Well, here's everybody. What's it going to be? I mean, it's going to be, essentially it's going to be the amount of, there's this many, each one's got a charge E, and just write it exactly the way they're writing it, guys. It's not, it doesn't really matter, but let me at least try to write it their way. All right, so you got it to here. Okay, that's fine. Let me, we know that dq is NE. Sure, we talked about that right here, among the first things. dq is NE. I agree. We know what N is. Put an E somewhere in that mathematical reality. And we have that. That's dq. Okay. Sounds good to me. Take a close look. Divide by dt on each side. Divide by dt on each side. Wait a minute. dq dt is the current. Divide by dt on each side. Yeah, it's absolutely the case. So if we have that, yeah, it would have been nice if I divided by the dt, guys. I said divide by dt on each side. Divide by dt here, divide by dt here. That's out of there. All right. Sorry about that. All right, so we got this. Absolutely true. You put the value, they kind of throw the vector in there at the end. I mean, we're not going to worry about it too much. We're going to say this. We're going to stay with that. Let's go with that. Let's take J in terms of magnitude, and J is going to be I divided by A, current divided by A, which is this right here, NE A V sub D divided by A. That's I divided by A. That's NE. The A's cancel. It's NE V sub D NE V sub D, throw the vector on there. It's the same exact thing we talked about here, guys. And then all the other reasoning that I relatively quickly just brought forth, building upon this and just building upon some other things that we knew about the E field and how it relates to force and just proportionality that goes on here. Strong E field is going to mean a strong current density, all other things equal. If the material is a good conductor, its conductivity is a big number. If it's a big number, this is indicative of this is the conductivity right here, right there. If it's a big number, yeah, J vector and E vector are directly proportional to each other for the mathematics that we're using here. And that's what we were talking about earlier as well. So that's some of the argument that's going on here with this. Let's talk. Let's look at some of the problems that have that are present for us to look at, and we'll kind of take it from there. Again, it's not too bad. I mean, there's much more to this, as there always is. But this is the basic stuff that they're telling us is right on the mark. It's brilliantly done by the authors, by Dr. Katz and by others. I mean, so it's good stuff for us. So as we look at this, let's try to see what we could say here, and we'll kind of take it from there. Let's take a look at problem number 20. From there, guys, I didn't mark the numbers I was going to do there, but I'm sure I'm going to have them there. If not, we'll always figure this out. But anyway, here we are. This is what we got. Okay, for number 20, imagine, for chapter 28, for number 20, imagine that you can change the thickness of a wire while the electric field in the wire remains constant. Suppose you double the cross-sectional area. What happens to A, the current density, B, the current, C, the number density of charge carriers, and D, the drift speed in the wire? Okay, it's a pretty fascinating question. Well, A, they're saying, suppose suppose you double the cross-sectional area, but you're keeping the E field in the wire, it remains constant. What happens to A, the current density? What does happen to the current density? Well, some interesting stuff happens. I mean, we know the J under consideration, they don't really talk about the area as much, but you got I over A, and we said that is sigma E. Okay, we talked about that. This is a constant. What does that mean? If you double the area, you got more current, given that the E field does what it does. Given that the E field is an unchanged E field, now it's just working with more content, with more material, with more charge carriers. How many more? It's a good question. For a given length over which this is running, there's double the area. You have double the area. You double the charge carriers. What does that mean? It's going to be double the current. Yeah, I know. You're going to get double. You may get double the current, but you got double the area. The twos cancel. You're back here. You still got the same J. So they're saying here, what happens to the current density? Nothing happens to the current density. What happens to the current? That's another story. What happens to the current? You just saw it. Yeah, no, that doesn't change, but 2I over 2A, that doubled. I doubles. The current, okay, so current doubles. Yeah, the area doubled, the current doubled if you kept the E field unchanged. I agree. Now what? They're saying, suppose you double the cross-sectional area. What happens to the number density of charge carriers? The number density of conduction electron, the number, according to, the people with the answer key and in our own common sense looking at this, the number density shouldn't change. The number of electrons under consideration or charge carrier or some other charge carriers under consideration, if we're talking about those imaginary positively charged carriers. Yeah, if you double the volume, you're going to, as a raw number, you're going to have double the amount of charge carriers. But what about the number density? The number density of conduction electrons, N, depends on the material and is constant. Yeah, you're going to have more of them. If you got double the, if you have double the volume, you're going to have double the amount of charge carriers, but the density of it won't change. Just like the charge, just like the current density didn't change. But you did have double the current. You did have double the current. But the current density did not change. The drift speed in the wire. The E field kind of calls the shots on that one, so there shouldn't be a difference. Everything on the right-hand side on these, so let's kind of see where we're at. You kind of play it a bunch of ways here. We say that J vector did not get changed with the discussion that we did. J vector equals N, that's a constant, that's a constant. Wait a minute, that's a constant, and that's a constant. The only way that side can be a constant and these two guys are constant is if V sub D is also a constant. V sub D in terms of magnitude, and I think they went more towards magnitude, is J vector is J vector over NE, and that's a constant. Constant, constant, constant. It's nothing other than a constant. That's all it can be. The product of constants is a constant, divided into a constant is a constant. Everything on the right-hand side of these circumstances is a constant. Okay? That's problem number 20. Look at problem number 33. Again, some of the ways that some of these things get mentioned can be a little, you got to use Occam's razor again, or at least have it clarified as to what assumptions you're allowed to make. That's so much of an issue in so much of what we do on this stuff. All right, let's see what they're having to say here for 33. Let me erase this, and we'll talk. They are saying two concentric metal spherical shells of radii A equals 4 centimeters and B equals 8 centimeters are separated by aluminum as shown in the figure. Now we'll draw the figure. The inner sphere has a total charge of positive Q at any time. If the two spheres are maintained at a potential difference of 2.0 volts via an external source, calculate the current from one sphere to the other. Well, it's going to go from the positive, which one's which? The assumption made, they're drawing the E fields, and I guess that's where the flow is going to be as well. If the two spheres are maintained at a potential difference of this much via an external source, calculate the current from one sphere to the other. Are separated, they're the two spheres, and they're separated by aluminum as shown in the figure. So it's just aluminum all over the place separating this thing inside the two. So what's going on here? So let's see what we can say and work some of the mathematics associated with it. Okay, metallic spheres, metallic spherical shells. And, the E field is going to point in the same direction as how the positive test charges will go. We're always working under the assumption we're talking about positive charges flowing and comprising the current, comprising what the current is. The charged particles for us, at least in the mathematics, they're going to be positively charged particles that are comprising the current and how it's going to flow. And the way that it's the way they drew it, there's a positive potential between the two, and apparently the E field is going in that direction the way they had drawn it. It's not something that's incredibly clear, or if it is, I'm not following it too well, but there's enough there that I think we're okay. Okay, so et cetera, et cetera. There's a lot, maybe more lines than that than what I'm drawing here, but these are the E field lines I think we're supposed to be thinking, and the charges are going to flow that way. The current, the positively charged particles for our conception of what's going on here, the positively charged particles, the current is going to flow in that manner. So if that's the case, there's a lot to be said here. Let me may end up writing a lot more than I need to write here, guys, but we know a lot. I mean, we know that E field is 1 over 4 pi epsilon naught. Q just is a general thing that we've been saying in the past. R hat, when we're talking about this, we know a little more synchronous with what we're talking about now, that J vector, the current density, is this. You know, it's always understood that we're talking about that, at least in terms of magnitude, and we can straighten out vectors later on, but at least in terms of magnitude, we're talking about that. The amount of current that flows is attained by saying, hey, get J vector, get dA vector, integrate appropriately, integrate the dot product. Notice those things we talked about regarding the dot product and the cross product are very important. In mathematics in general, specifically in physics and in engineering, it's there quite a bit. We know that. What's going on here? Well, we know that sigma times, sigma times E will give me the J. Sigma is a constant. We've got that. Yeah, true story. Let's can we talk about it? I mean, we got the way they got it set up. Let's talk a little bit and see what we can say about it. Using that right there and plugging in for E, you know, the appropriate integrals are, we'll deal with the appropriate limits of integration and things like that. We'll figure it out. 1 over 4, you know, it's maintained at a Q. So when you're over here, it's a capital Q they told us it was maintained at. So the little q just call capital Q. Yeah, it's EDA, right? I mean, when we say EDA, well, the 1 over 4 pi, the 1 over 4 pi epsilon naught, bring it out. You know, not bring the 1 over 4 pi epsilon naught comes out. There's just a capital Q in there, and the capital Q comes out as well. I mean, basically what we're doing here is, for the E vector, the Q over 4 pi epsilon naught comes out of there. You got 1 over r squared underneath, and that's where the integral is going to be taking place. We are talking about, they're parallel to each other, so the dot product is equal to 1, so that's not an issue. And we can, you know, and it's going to be the same throughout. So this integral, really, each one of these dAs that are associated with it, the differential area for a particular place under consideration is 4 pi r squared. So you've got, yeah, there's a bunch of ways you can hit this, I guess, if you want to do this. You know, you could say a bunch of things here, guys. You could say that for this right here, 1 over r squared, the dA is the differential element of area under consideration is, yeah, I mean, it's got get a little messy on that point. The big, you're probably much better off not going there with that. It'd be a hard thing to decipher, but the bottom line is this. This dA, the big thing here, this dA is part of 4 pi r squared. It's part of it in terms of it's a differential portion in a sense. It's a differential portion of this, and if you integrate all of it, you get back to 4 pi r squared. D as in a differential right here. Okay. Make a long story short, because of the great symmetry that's involved pertaining to spheres, wherever you're taking the R to consider the dA associated with it, the R is basically the same everywhere for a given value of R, and the dA, when you add them all up, is 4 pi r squared. So at the end of the day, it's not, at the end of the day, you're getting this. You get this, 4 pi epsilon naught, and you had, like I said, you basically got 1 over r squared dA plus 1 over r squared times another dA plus 1 over r squared times another dA. Well, you take the 1 over r squareds out of there and add all the dAs, and you get 4 pi r squared. It's a little on the messy side, but you get somewhere here, which isn't too bad. When you do that, the r squareds cancel. You got 4 pi here. The 4 pi and the 4 pi cancel as well. You got sigma q over epsilon naught. Absolutely. I mean, there's a number of ways to go here. You can also observe that this, and you'll see more in the notes when you do it. You can also see that Q over epsilon naught is E vector dot dA vector. Anyway, it's kind of rather interesting. You're going to get this according to Gauss's law anyway. That right there is going to be capital Q over epsilon naught. Multiply it by sigma. Well, it's capital Q over epsilon naught times sigma. So it works out pretty nicely. It's consistent with things that we've learned in the past as well. So we've got this thing. We've got it. There's more notes on there. You'll see it more when you look at what I'm saying here, guys. I wrote this in a I think this is. I end up getting a negative answer on this thing. There's ways to do this to actually find what's going on. From high potential to low potential, the magnitude is this, and we call it that. Okay, let me. I'll go a little bit. What I did in the notes is okay, but it wasn't the best thing to do. You're integrating from A to B regarding what's going on here. So you're going. Essentially, what's happening is going from low potential to high potential, but we already know that the high potential is associated with. We could essentially say we're assuming the high potential. The way I did it in the notes is a little more. Is not the best way to have done it. So let me kind of go away from what I did. But the notes should be clear nonetheless. You go on the E field is this way. We're also going to say high potentials here, low potentials there. High potential to low potential. Work the E field, see what happens. What does happen to the E field? Well, according to what we know, as you're going to get to here, the charge that's contained, the E field loses strength as you get up there. So when you're integrating that, let's see what happens. You didn't need to put I put a negative on there and I probably didn't really need to. There's things you do. If you went B to A, the final to the initial, that'd be the way to do it. you could write it like this, and I didn't quite do that. Negative of, from big to small to find out what kind of potential you're talking about, work it like this. That'll definitely work. At that point, why not just make it easy and just turn this around, and that's the opposite of this, so just do this. So if you're going to do the E field, it's an E field, an increasing E field, and you're going from small to big, small radius to big radius. Can you find out what's going on? Yeah, absolutely you can. That's probably the easiest way to go. It's always these things regarding potential. You got to kind of watch your step on it. Oftentimes, you're almost always, if your math is pretty solid, you're going to get the right magnitude. But if you quite didn't follow the standard format of finding that potential, you might get the right magnitude but be off by a sign. Usually no more than a sign. So kind of just watch it. That's one of the things you want to show some savvy on, I guess. We all want to, myself included, we have to show some savvy on it when we're doing something like that. They're saying this right here. What's going on? Basically what you're talking about is V is equal to the integral from A to B. You heard the argument already. E vector dot dr vector, all E vectors and all dr vectors are parallel to each other. All E vectors and all dr vectors are parallel to each other, so the dot product is always 1. The dot product is always 1 between them. That's good. That makes it a lot easier to look at. We know from Gauss's law that we can have the E field expressed as follows. And that's it. I mean, that's about where you're going to go, guys. You're going to go right there, and so you got this, and when you do the integral here, you end up getting, look, the Q and the 4 pi epsilon naught are all one big elaborate constant. That's not a big deal. You're integrating 1 over r squared, and that's where you get the negative over r. The negative, it's negative 1 over r. So negative Q over 4 pi epsilon naught over r evaluated between A and B. So you got that. Okay, sounds good to me. This is where it kind of works out real good that way. You sort of get a feeling what you can use to actually find the potential, to be calculating energy, potential differences, and things like that. The magnitude's a big thing, and then having the instinct to know, okay, was my direction of evaluation okay, or do I have to kind of watch out here? At most, you're going to be off by a sign, and you should be able to catch if it didn't go right for you. So just watch the setup on it. It can get a little confusing. Here we go. You got B here, you got A there, you got a negative here. You got V is negative Q over 4 pi epsilon naught. You'll see what I mean in a second here, guys. I'll get just messy sometimes. That's 1 over, just take that out of there, and just evaluate the R. It's 1 over R. That's 1 over B minus 1 over A. Yeah, I know, you got a negative here. Why don't you multiply by negative, take this negative 1 and bring it right next to this quantity and go negative 1 times all this, and you get 1A minus, you get 1 over A minus 1 over B. So you saw what I did, and that's about what we wanted. That's what we wanted, because A is small. Yeah, 1 divided by small is big. B is big. 1 divided by big is small. So 1 divided by small, big. 1 divided by big, small. Big minus small, positive answer. Yeah, that's what you just kind of watch out. You can, and in the notes, I kind of got a little bit careless. So, but then you can land on your feet. You just got to be careful. So let's see what we got here, guys. We set it up in such a way. Right. Okay. So I'll tell you what. At that point, can you tinker with this a little bit more? Yeah. I mean, multiply by a special one called B over B right here, and that's B over AB. And multiply by a special one here called A over A, and get A over AB. So you got B over AB minus A over AB. Okay. B over AB minus A over AB. You got a common denominator. Write it down. All right, that could be useful. I mean, we've compacted it in a sense. We've made it so we don't have fractions all over the place. We got one big fraction, a bit awkward, but it's one fraction. It's not two fractions. It's a little bit easier to deal with. So that's good. I mean, so what you say there is, and current will flow from high potential to low potential. So the magnitude is what we talked about. And like I said, I straightened it. Here I did this without having to kind of straighten out and get in absolute values. But in the end, I caught myself here in the notes. And you can catch yourself too if something doesn't go right. You've got the right magnitude. Just make sure you got the right sign associated with what's happening there. They are telling us, I mean, they're telling us a lot of things, I guess you could say. We could say that we've got what I is, and we could say a whole, let me try to keep it right. It should be, okay, all right. Okay, so what do you want to say? You know what? Okay, we got this. That's a pretty big thing. We've got I equals sigma over Q epsilon naught. Okay, we already talked about that. In fact, there it is. I mean, we'd already derived. We discussed it, we derived it, we looked at stuff that was going on. Yeah, it looks pretty good to me. I mean, it looks pretty good to me. We've got this, it's believable, it's absolutely believable. If there's a lot of charge and a great amount of conductivity, it's associated with a lot of current flow. Okay, take it at that level. And also we've done other mathematics and reasoning to actually get that. We've already done that to get that. So what do you want to say about this? Well, the way you want to look at it is just solve for Q, given all this stuff you've gotten. Leave Q alone, multiply V by 4 pi epsilon naught, and then multiply each side of this equation by 4 pi epsilon naught. Then multiply each side of this equation by the reciprocal of this fraction, and that'll get you Q all by itself. And you got, what do you got? You got AB, B minus A. I got the AB in front in the notes. That's not a real big deal, guys. For some reason, I could have, okay, yeah, everything's okay. That's correct, that's fine. And then we say, well, what, now by solving for V, by solving this equals for Q, we got all that. What's I going to be? We already said what I is going to be. I is going to be sigma. Where's Q? It's that entire song and dance. Yeah, looks pretty good. Let me actually, yeah, okay, there's nothing wrong with that, absolutely. Yeah, absolutely, that's fine. So you're looking at that. The Q's on top. For some reason I thought I was going to be doing some kind of dividing. The Q's on top, way over there with the I thing. So with the Q on top, that's not going to be an issue. We do see it's about the end of the story, guys. Yeah, I mean, let me write in the order that I've seen it written elsewhere. It's not a big deal. The big thing is just have this thing down and have it right. 4 pi sigma ABV over B minus A. It's a pretty fascinating discussion in its own right, is what it is. You know, this AB divided into BA is the same as the quantity 1 over A, the small one, a bigger answer, 1 over A minus 1 over B. This is the reciprocal. So the reciprocal of this is what we said, right? I mean, so you're looking at it, you got that. Right, exactly. I mean, it's the way the whole thing played out, you guys. That's of interest. So basically, if the difference between these two is very big, that's indicative of this being very big. If the difference between these two is very small, then this is very small. Well, divide this very small thing into here, you'll get a big answer. Now, the only way you can get this to be really small is if these two are very close together. If these are close together, the closer the walls are, the smaller the answer here, the smaller the answer there. Yeah, I mean, there's a whole lot you could say here, and then if you're dividing by this reciprocal right here is the reciprocal of this, and it's the reciprocal of that. Well, that reciprocal is going to be a real big answer if these guys are close together. Well, yeah, given what's going on there, I'm trying to actually just say, the closer they are together, I guess you could say. There's so much you could say here. But minus B for a given potential, here's going to be your biggest answer. So, because you're subtracting something as well. Okay, there's a lot to look at. There's a lot of math, depending upon what they could ask us, there's a lot we could say. The big issue here. But the numbers are the numbers. I mean, that's just it. And whatever, now, what has to happen for that manifestation to take place, I mean, whatever. But 1 over A, 1 over B, for a potential to do work, if, you know, there's more work that's going to be done. There's more work that's going to be done if they're further apart. And if they're further apart, the answer that you're going to get is going to be a bigger answer. If they're close together, it's a smaller potential. There's a whole lot to be said here, guys. We can look at. But again, you look at how this behaves, okay? And the way, if you're going to get, just on the side here, guys, I don't want to go too much into it. They're not going into it, so I think I'm kind of being a little foolish going into it right now, because we could be asked a number of things, and we could answer them about a particular function. But A times B over B minus A, that's, you know, maybe not an easy thing to visualize. However, you know, the quantity A times B over the quantity B minus A is the reciprocal of the quantity B minus A over A times B. Yeah, that's great. What is it telling me? Well, that right there came from this, and this can give me, I can figure out a way to get a big answer here, which would be the same big answer obtained here, which maybe isn't that easy to look at here. Maybe not that easy to see, but here I could get a big answer. The reciprocal of it would be all of this underneath a 1 over the quantity 1 over A minus 1 over B. And there's stuff we could do with it. Okay, they're not asking that. They're asking to here, or actually, they asked that, but I mean, the real big thing, our answer, I think they're looking for current more than anything here. Can you get it? Well, okay, yeah, the current, huh? 4 times pi times sigma times A times B times V that we're told is there, divided by the quantity B minus A. Interesting. Plug in the appropriate numbers that they've given to us, guys. Convert to the MKS system of units. We're getting a rather remarkable number here. So 7.6 times 10 to the 7th amps. 7.6 times 10 to the 7th amps. Remarkable, yeah. 7.6 times 10 to the 7th amps, which is 75 million, or at least on the order of, they're both on the order of the same magnitude here. This is more of an approximation. What we got was 75,740,000 amps. So, rather fascinating. For 34, a battery is connected across a conductor that has an irregular cross-sectional area as shown in the figure. And I can kind of maybe draw that for you. A is the rate of flow of electrons per unit area at point A less than, equal to, or greater than the rate of flow of electrons per unit area at point B. They're connected to the same battery, guys. That's an important thing here. B is the magnitude of the electric field at A less than, equal to, or greater than at B. So they got A and B here. Let's just see what they have to say. We know, based on the data that we have, the information that we have about J vector, about sigma, the conductivity sigma, the resistivity rho, J vector, the current density is J vector. What we know about E fields, things of this nature. What's going on? All right, they got two setups here. something like that. You got a cross-sectional area here. Called, whatever. There's a cross-sectional area here. Let's just call it A, or at least, and you got a cross-sectional area here. Let's call that B. And you've got the whole thing hooked up to a battery. Okay. In our conception of what's going on here, we're assuming the flow of positive charges, as we've already said. Okay. So it's looking something like that. It's how this thing looks, right? A battery is connected across a conductor that has an irregular cross-sectional area as shown. A is the rate of flow of electrons per unit area at point A, the big area, less than, equal to, or greater than the rate of flow of electrons per unit area at point B. B is the magnitude of the electric field at A less than, equal to, or greater than is the magnitude of the electric field at A less than, equal to, or greater than that at B? Okay. So there's a lot you can say. Let's proceed to say it, I guess. I is the same everywhere in this conductor, so a bigger, larger area means, so I guess you could, this is location A, location B, and we can talk a little bit. I is the same everywhere in this conductor, so a bigger, larger area means, as far as the charge density is concerned, you can write it as, as far as the current density is concerned. The big thing is, once this all establishes itself, in aggregate, the amount of current that's flowing, regardless, you've got it set up, there's a flow of current. The flow of current is essentially, after all is said and done, is constant everywhere. I is the same everywhere. The flow of current is the same everywhere. Flow of current is the same everywhere. I is the same everywhere in this conductor. So a bigger, larger area means the following. This is the bigger area, and that's a smaller number. When you're dividing by a big number, big area, you get a smaller answer than when you're dividing by a small number. What does that mean? Regarding charge density, that is significant. Current density at A is less. The current density here at A is less than it is at B. Simple as that. That's A. For the other one, they're talking about the magnitude of the E field. So what's going on here? Well, we said you're going to have a really big E field if there's a lot of resistivity and you still have a big current density. Yeah, true. Do you remember this conclusion? We just drew it. Therefore, you take this guy, multiply it by a constant rho, take this guy, multiply it by rho, take this guy, multiply by rho. They're positive numbers, so there's no reversal here. You got that. What does that mean? Well, that's E sub A, that's E sub B. There's a stronger E field for the current to get through there. Man, there's a stronger E field. Resistivity, is the same. We're not saying anything different there, but you're getting a lot of current through there over a small area, and that cannot be the easy thing to do. So, and they're saying that. For 34. E sub A is less than E sub B. Is the magnitude of the electric field at A less than, equal to, or greater than that at B? At A, it is the magnitude of the electric field at A less than, equal to, or greater than that at B? It is less than that at B. It is less than that at B. Yeah, because B has a small area there. There's a lot getting through there, as much as getting through anywhere else. Same current's getting through there. And to be able to do that, there better be quite the E field to get it with all that's going on in that confined area. Is a real good explanation for it. So you got this, and this is B. Okay, let's go to a few other problems here, guys. Let's go to 76, 77, 80, 81, 82, and let's see what we can do here. All right, guys, for 76, for problem number 76, a 1.50 meter long wire of aluminum is constructed such that it has inner and outer radii as shown. A potential difference is maintained on either end of the wire so that current I is from one end of the wire to the other. Find an expression for the current density as a function of I and the two radii R sub A and R sub B. Well, okay. I mean, the look of it is, we're looking at it coming right at us, I guess you could say. That's R sub A. That's R sub B. Okay, this is right there. That's R sub A. And right there, that's R sub B. And it's just it's a wire, and they're asking, a potential difference is maintained on either end of the wire so that current I is from one end of the wire to the other. Find an expression for the current density as a function of I and the two radii, R sub A and R sub B. So, pretty straightforward stuff, guys, actually. It's the lead up to it seems to be a little more complicated in the actual process. The amount of area you got, it's hollow right in here. Whereas this is, is where the substance is, I guess you could say. And in there, it's hollow. So, the way they put it, I mean, there's a number of things that are not said, but it's kind of understood here. It's constructed that the inner and outer radii are this, maintained. There's not a whole lot of discussion pertaining to it, but the assumption is it's hollow in the middle. So, but everything else has substance to it. So what do you got? A is pi r sub B squared minus pi r sub A squared. So pi r, the big radius is r sub b, the small radius is r sub a. Pi r sub b squared minus pi r sub a squared is this. The rest is pretty straightforward, you guys. I mean, you've got that. J is I over A is I over, and that's the end of the story, I think. I mean, that's as simple as that when they write this. The magnitude of the J vector Okay, that's it. Yeah, that's all they're asking on that one, guys. For 76. For 77, not really difficult, but be careful. I mean, as well, just be careful with it. For 77, consider a situation described in problem, consider the situation described in problem 76. Find an expression for the drift velocity of the electrons flowing in the wire as a function. Okay, so consider the situation described in problem number 76 find an expression for the drift velocity of the electrons flowing in the wire as a function of I, the number density, small n, and the two radii, r sub a and r sub b. Can we do it? Yes. I mean, pretty easily, actually. You just got to be aware of the equations that we looked at and derived and said, wait a minute. We remember in terms of just the magnitude of what's going on here, the charge density is going to be, forgive me, not charge density, the current density is going to be equal to the charge density per unit volume times the charge on each one of the charges in that volume times V sub D. What's going on here is you've got essentially very, very many charges per unit area. If you multiply it, very, very many charges per unit area, and so small n per unit volume rather. So J, the current density is equal to the volume charge density times the charge per charge carrier times the drift velocity. What's going on here? Well, this is the number of charges per unit volume. You multiply by the charge per charge carrier. That's the total amount of charge per unit volume. If that volume, with that volume itself, if that volume of charge, that unit volume of charge is moving, or you say that there's a particular volume of charge that in aggregate is going to move at a particular amount of speed per unit time, a particular distance per unit time, all of them are going to cover that distance. So that entire volume, that entire volume will pass a particular cross-sectional area. Well, what is that? Well, if you say, this is the kind of an interesting point here. If this is the total number of charges per unit, total number of free charges per unit volume, and this is the total, and this is the charge per charge carrier. So total number of charge carriers per unit volume, and this is the charge per charge carrier, multiply the two, and that's the total amount of charge per unit volume. We're assuming they are all moving at a speed on average, each one of them at a speed on average, each one of those charge carriers moving at a speed on average of V sub D, which means a distance per unit time. Well, if all of them move a particular distance, there is, let me just try to give you a good visualization. We already derived this, but I just think it's important to kind of look at it another way. If you've got a particular distance that gets traveled, you're talking about, well, you're essentially saying that for a particular cross-sectional area, this right here is just saying there is n total charges per a particular. Let's say let's say there's a constant cross-sectional area throughout. Total number of charges here. Total number of charges in a particular circumstance. So let's put it this way. Let's say so we got J. Well, we'll see that it equals J. And J, we're making the claim that we're trying to get J, which is equal to the current per area. The current per cross-sectional area, that's J. J, the current density is amount of current passing per cross-sectional area. And that is essentially amount of charge per unit time. So let's say you kind of, it's not a real big charge, but let's say amount of charge per unit time per area. Okay, sounds good. We know that amount of charge is N, the total amount of charge that actually went through, N times E, the whole thing divided by T over A. We know that you could say that this right here is charge carriers per unit volume. So that's going to be equal to charge carriers per unit volume that's the amount of charge per unit volume times volume divided by time. Okay. The volume, as this thing moves, if it's going with an average velocity v sub d per unit time t, it'll take out a volume, this right here, which is NE, total number of charge carriers, total number of charge carriers per unit volume, times E, total charge per unit volume, times V. And V is, it's crossing a cross-sectional area, AD. It's gonna cover this much volume in a time t when it does it. Divided by t, it's going to do that in a time t. And here's the A. It's going to cover a particular amount of volume. How much volume? The cross-sectional area times the amount of distance traveled in a time t by every one of the charge carriers. Yeah, that distance, L, is V sub d times t. That L is V sub, that L is the drift velocity times t. It'll cover that L. All of them will cover that L. Well, all of them will cover a volume. They'll hit at some cross-sectional area, and after a time t, they will cover a distance L. All of them will. So that much volume of charge has moved. That much volume of charge has moved times the amount of charges per unit volume. That much volume of that much volume of however much charge is in there, that much volume of charge has moved times the number of charges per unit volume will tell you how many charges have moved, times the charge per charge carrier. That's the amount of charge that's moved. Sure. Divided by T, that's I. Divided by A, you got J. Wait a minute. You had an A here too, though. Yeah, you had the A right here, because this guy was the L. That guy was the L. T goes, A goes, N, E, V sub D. Yeah, I mean, it's not pretty. I mean, like as we said, we're making the claim it's going to look like that. Indeed, it will. There's an A here, NEAL AL. The L movement of everybody means a volume has moved of this much. And that much volume has moved in time t. We had A down here because we were dividing. Well, that's it. I mean, this is the amount of volume that's moved in time t. That volume times the number of charge carriers per volume is the number of charge carriers, period, capital N. Times E, that's the total charge in time t. All this divided by t, that's Q. All this is Q divided by t, that's I. Divided by A, you got I divided by A, that is J. Wait a minute. This L over T is V sub D. These cancel, and that's where you're getting that. And that's where you're getting that, guys. I'm afraid I don't have enough room here, but for as large as I like to write. Here's A, they go. You got N, E, V sub D. Yeah, we already derived that. We derived it in a somewhat different way. In a somewhat different way we derived that, but there it is. Have no doubt about it. And that's a lot, and that's much of the bread and butter of what we're talking about in this chapter, as we've already said. Absolutely. So let's see. We're saying that. Well, how are you going to do it then? Fascinating concept. I mean, we've got all this other stuff, all this background with it. Let's keep going with 77. You got this. What's V sub D? You're looking right at it. I mean, in all that process going on, guys, in all that process going on, we got J equals NE V sub D. J equals NE V sub D. V sub D equals J over NE. So far, so good. What does that mean? It means what we know. V sub D equals I. What does V sub D equal? Isn't J I over A? Isn't J I over A? Okay, here's I. Put the A down here. Well, I'll put the NE. Then I'll just put the A. And that's 77. And that's 77. Let's go to problem number 80. We'll talk about that. Let me get a little bit of a setup on this, and we'll figure it out. Let me give 1 second. I'll just take a little break here. Okay, guys, welcome back. Let's finish this out. Problems 80, 81, 82. Let's deal with it. Let's do problem number 80. Two long concentric cylinders with radii A and B are separated by a material with conductivity sigma that varies as sigma of R equals K over R, where R is greater than A. where r is the radial distance from the axis of the two cylinders and k is a constant. A steady current I flows radially between the cylinders. Find the resistance between the cylinders. Assume the length of the cylinders is capital L. Okay. Well, look, let's just start the whole thing out. I mean, J equals I over A. We've been into that already. This is a variable quantity in this case because A increases as we move outward radially. What's going on here? Well, it means this. The A on the bottom is the circumference of the cylinder times the length. That'll give you the area at a particular radius, that is. So 2 pi r L on the bottom. We know from prior discussion, even and certainly from in the intuitive sense, we know that J equals, or at least we can believe that J equals sigma E. So E equals J over sigma. Sounds good to me. Basically, we said what we said here. Let's see what else we can say. If you're going to talk about this, we know that, okay, well, let's state some obvious stuff. If J equals sigma E, and if J equals this, and of course, we're talking about the same J in both equations, J equals J, we're here. We got sigma E equals I over 2 pi r L. Sounds good, sure. What does that mean? Well, we could talk about an E field at that point. I mean, the E field is going to be, let me just kind of write it kind of the exact same way, I guess you'd say. That's the sigma, right? So we can divide by sigma. So we got I over 2 pi r L. Yeah, but for sigma is equal to some constant divided by r. As r gets bigger, k over r gets smaller. The conductivity at a particular r is different than the conductivity at another r within this region in which they are talking. The more you go outward, the conductivity decreases. Pretty interesting. So let me just, okay, we got that. Yeah, it looks pretty good. We've got this. I'm sorry, I should have put a sigma right there, and there it is. And we know sigma is this. Sure, okay. Well, if that's the case, K over R is this, and okay. So how does that all play out? Well, look carefully. This is K over R. K over R. Here's the R there. This R and that R cancel. You've got E equals I over 2 pi K L. The 2, the pi, the k are constants. The k is a constant in this circumstance, right? So for the problem, it's a constant. The 2, the pi, the k are constants. L's a constant too. Yeah, that's pretty fascinating stuff how that all happened. The k over r, like we said, the r down here and the r here canceled. That's yeah, I mean, it sure looks that way here. We got a 2, a pi, a k, and L. The 2, pi, k, and L are all constants. The product's a constant. We got this. There's your E field. Well, sounds good. So I guess the way you'd want to do this is, again, it gets kind of touchy with this, but let's figure it out. You're going from the far away to the close, so you're going to go like this, and everything should kind of come out for you. Let's see if we can believe it. The far away to the close, you got this. That's the same as negative of this integral is the same as positive this integral. E vector dot dl vector, which is the integral from a to b. So we went from the far to the in. We're claiming the E field. I mean, we're defaulting, I guess, to what we think the E field is here. How this is working out here. There is a positive conductivity. It's a constant, or is it? I mean, we don't know what K is either. But the way this should all come out, yeah, this should be positive anyway. That's not an issue. So what we have is, well, let's see what I is. 2 pi k L dr we're talking about radius. There's not a whole lot to say there. I get the way we're looking at it. I mean, there's a lot to be assumed here. As this goes, the current, a steady current I flows radially between the cylinders. Find the resistance between the cylinders. Assume the length of the cylinders is capital L. A steady current I flows radially between the cylinders. So we'll make the assumption it flows from the inside out, and it's a steady current. If that's a steady current, guys, steady current, that means that's constant. So is that, so is that, so is that, so is that. The whole thing's a constant. It's a constant E field. So it won't be surprising that we're getting the answer we're about to get, at least regarding the E field. So let's see what we got here. You do it. It ends up giving you I over 2 pi KL. I over 2 pi KL R evaluated between A and B. That's gonna be and that was the voltage, right? So that's the potential difference, and we're saying, okay, let's figure this out. We're going, we're claiming we're going into something, and we're having to fight against it. So the negative is what's going to give me the answer I want. It's a negative value, negative of a negative. That would be positive. If this was going outward one direction, this is going diametrically. And this is a collinear, but diametrically opposite to it. It's a negative. Negative of negative is positive. Going from B to A, yeah, you're increasing potential. That's how it works. As you look at this, yeah, I mean, the way it's going to be for an answer, pretty straightforward stuff. I mean, it's going to be I over 2 pi KL B minus A. So that's the potential difference. So let's see what we got here, guys. I'm going to put it as based on the assumptions I made. If it were the E field coming out at me, then me to go into the E field requires a positive amount of work. If you're going to do the dot product, however, the E field goes one direction, the dl goes the other. They're diametrically opposed to one another. The cosine of pi in radians, or the cosine of 180 degrees, cosine of pi in radians equals the cosine of 180 degrees equals -1. You're going to get a negative answer, then you go negative of a negative, positive. Oh yeah, you did increase potential going in there. So that's kind of the scale. That's kind of how they scale it, you guys, to actually talk to you about doing it. If you draw blank sometimes, you get the magnitude and say, well, what's going on here? Well, how much potential difference is between the two? Well, I'm going to say that A is at a higher potential than B. At least that's how this assumption works out. for what we're trying to do. So what do we got here? We got V, the whole thing here. Yeah, that's the potential difference between them. What's the resistance going to be? Resistance can be pretty basic, guys. The resistance, we know that potential difference is I times R. Potential difference is I times R. So the R is going to be voltage over I. That's going to be the resistance, voltage over I. So let me take this voltage and divide it by I. So resistance equals potential difference divided by I. I think we know where this is going, guys. I mean, we got 2 pi k capital L B minus A. Well, all of this is V, all of this is I. 1 right here. One right here, yeah, one right there, you know the deal. Yeah, that's it. That's the resistance, guys, at the end of the day regarding that. That is the resistance. Let's go to 81. 81. A generating station and a switching station 140 kilometers away are connected by a high voltage aluminum transmission line that has a current of 850 amps. Each wire of the transmission line has a cross-sectional area of 750 square millimeters, and the density of free electrons in aluminum is 6.022 times 10 to the 28th electrons per cubic meter. How much time does it take for one electron to travel from the generating station to the switching station in this wire? Okay, so this is pretty interesting. You know, so there's a generating station and a switching station are 140 kilometers away are connected by a high voltage aluminum transmission line that has a current of 850 amperes. How much time does it take one electron to travel from the generating station to the switching station in this wire? It's got to travel 140 kilometers. That's 140,000 meters. So a number of things we have to look at. Should be pretty basic though. So let's see how we can do this, guys. Essentially, let's just walk through it. The distance. (140 kilometers) equals 140,000 meters. I equals 850 amps. The area they already told us. I mean, it's 750 square millimeters. 750 square millimeters, huh? Yeah, every millimeter is a thousandth of a meter. A thousandth of a meter times a thousandth of a meter is, let's figure this out. I mean, it's basically what they're saying. Let's make the switch. I mean, if you're going to go to square meters, every meter has 1,000 millimeters. A square meter is 1,000 millimeters times 1,000 millimeters. There's your conversion. A equals 750 times 10 to the negative 6 square meters. Okay. They're telling us that the density of the electrons per cubic meter electrons or something similar to electrons, same exact charge, right? Positively charged. Yeah, we know a lot. We know, here we go again. We know that J is I over A. We know that J vector is NE V sub D vector. We know that in terms of magnitude, we got J equals IA. I'm sorry, J equals I over A. J equals I over A, and J equals NE V sub D. Well, true. J is the same in each equation. So if that's the case, the I over A, and that's what's going to get you through it. The I over A J equals J, so this right here and this right here are equal to each other. So we got I over A and E V sub D. V sub D equals I over NEA. Solve for V sub D, divide by NE on each side. That's it. I mean, that's maybe the hardest part of the whole problem. Once you get to here, how much time is it going to take? I tell you what, I mean, isn't distance equal to speed times time? You know, v sub d is what we're talking about, and that's the distance d. I don't like. I mean, it's a little, you know, whatever the distance is in this case. I mean, I think I might have written it. Yeah, I mean, that's how I wrote it. I guess I'm just not. D is in distance, and v sub d for drift is that. T is going to be distance divided by v sub d. T is going to be distance divided by v sub d. That's going to be distance divided by v sub d, which is all this. Divided by v sub d. Put this on the bottom. It flips. You got NEA on top and I on the bottom. Sounds good to me. They gave us various numbers here. Let's work with those numbers. They told us what the area was, and we found the area. The area is 750 times 10 to the negative 6. 750 times 10 to the negative 6. E is 1.6 times 10 to the negative 19. Small n is 6.022 times 10 to the 28. And D, the distance between them is 140 kilometers, which is 140,000 meters. I is 850 amps. Well, we have to make sure to use the MKS system on everything. We do. Plug all that in, and let's see what happens. Quite a bit. I mean, it's going to be in terms of seconds, and then we got to, it's probably a good idea to figure it out in terms of something other than seconds. This is something else. This is 1,190,230,588 seconds. That's roughly 37.74 years. It's a lot. But we did the math, we followed the equations, and we got the answer. Okay, that's 81. Let's do the last problem in this set, and that's 82. For problem number 82, a conducting material with resistivity ρ is shaped into a wire of length small l with a tapered cross-section that decreases from radius r1 on the left end to r2 on the right end. If the current density on the wire is a constant as a function of the horizontal distance x along the wire. So if the current density in the wire is a constant as a function of the horizontal distance x along the wire, what is the resistance of this tapered wire? Okay, let's take a look at that. So they gave us enough information that we can handle this. We know enough pertaining to this chapter that we can handle this well, and they gave us some specifics that are going to help us really give a good answer here. Even if the numbers are not like very specific numbers, they're more just a symbolic, they're using letters rather than the actual, they're using non-numeric symbolism to talk to us regarding this, but we know the physics that is required, the mathematics that is required to view this. So I think we're going to be okay. Again, a conducting material with resistivity ρ is shaped into a wire of length small l with a tapered cross-section that decreases from radius r1 on the left end to radius r2 on the right end. If, and it does so in a linear sense in a way, you'll see when I draw it. If the current density in the wire is a constant as a function of horizontal distance x along the wire, the current density in the wire is a constant as a function of the horizontal distance x along the wire, what is the resistance of this tapered wire? So, let's take a look. Kind of does so in a linear sense, but it tapers off. Here it's R2. Here it's R1. The length, center to center, is small l. It's a conducting material. This is not a great drawing, I know, but it's basically what the book's got a better drawing of it, but it's essentially the same thing, guys. Let's talk about it. We know enough. Well, we know that the resistance of a wire is directly proportional. We know that the resistance of a wire is directly proportional to the kind of material that it is, and it's directly proportional to the length. The longer the wire is, the more resistance is going to be associated with it. It's harder for the electricity to move if it's a long wire. And the bigger the cross-sectional area is, that's also going to make, and the smaller the cross-sectional area is, so a small cross-sectional area and a long wire, big divided by big is huge, big resistance. If it's a short wire and a big cross-sectional area, small divided by big is tiny, small resistance, so on and so forth. That's one thing to keep in mind when we're doing this. We know they told us J is not going to change going across like this. We can find a formula, a general formula, for the radius somewhere here. Whatever, I'm writing it here, but the radius here, the general radius r. How can we do that? Well, this thing falls down, it tapers in a linear sense. What does that mean? That means that if you were to take a look at big R1 right here and small r2 right here, and if you were to run a distance of L, I don't know how good this is visible, guys, sometimes, so forgive me. I'm kind of It's a horizontal distance. This is not a good, obviously this is not you mean a horizontal distance, but let's just say it was. Let's say it was a horizontal distance. If you went L across, you dropped from R1 to R2. In other words, this thing was height R1, and this thing is height R2. And the difference between the two is this. It dropped R1 minus R2, and it ran L. Well, if it's a drop, it's not a positive slope, it's a negative slope. What's the slope? The slope is rise over the run. Well, that ain't a rise, it's a drop. What's the drop over the run? R1 minus R2 divided by L. It's a negative though, because that's a positive number. That's a big number minus small number. So go negative the quantity R1 minus R2 divided by L. That's the slope. And when you do that, that'll get you the value of x. And x would be equal to, I mean, there's a lot of ways to write this. Times x, that'll give you the new r. Well, what is the new r, guys? It's this guy plus the drop-off. What is that? Well, the new r is this guy, and you ran a distance x. I mean, and the whole distance x is L, but you just ran a distance x. Yeah, I know, but I want to find out what the slope is. Well, the slope, we said, here's where it gets interesting. Now, here, the way I ended up doing it, I went the other way. I could go this way and I could climb. I think the way I was trying to go, yeah, I used, you know, there's a lot to say here, guys. Let's indeed rise. I mean, it's a drop. It really is a drop if you go from left to right, it's a drop. But if you go from right to left, it's a rise. Let's take our walk this way. Doesn't matter which way we take our walk because the r is going to be the same no matter which way we go. Okay, let's go this way. Perhaps it was easier. I thought it was easier when I first did it. Do I think that now? That's neither here nor there. The radius r is, if you take a walk of x away from R2, so don't do this. Took a walk of x from R2. I guess we got to use R2 as kind of the okay. Okay, now I really hate myself. Yeah, I did have it set up in such a way that it was going to fall the way it's supposed to fall. Let's look at it again. Forgive me, guys. Let's take that walk again, and let us go. Let us indeed go from x equals 0 into positive values of x. Let's keep it that way. That makes sense. I just read it wrong, guys. If this is x as you walk from left to right, there is going to be this right here, R1 minus R2 is a number that's positive because R1 is bigger than R2. Okay, I'll tell you what I'm going to do. If it's a drop, let's do this. R, this radius here, you guys, under consideration, this radius right here, R, is after the fall down. So what do you do here? Let's start at R1 and let's do a fall down and see what happens. Well, you'll see what I did in a second. We're going to go R1 is big. plus a negative positive number. R1 is big, R2 is small, over a length L. That's the rise over the run. You got to put a negative there to get the drop. And that's what it is when it's with X. And that's what it is when it's with X. That gives you negative of this is R2 minus R1. R2 is the small radius, R1 is the big radius. Small minus big is negative. Okay, you got your negative slope. Same absolute value before you put in same absolute value. This is just this right here is positive. That makes it negative, and that's the negative 2 when you flip it around that way. Okay, that's the way I had initially written this down. I thought for some reason I thought R2 was bigger than R1, and it's not. R2 is the small one, R1's the big one, and I tried to kind of call an audible on this thing, and not a good idea. I should have just stayed with my notes. But this is what my notes write. So you've got this to get any R that you need. Sounds good. We talked about this. Keep talking. Well, I'll tell you what, the cross-sectional area is its own business, and there's just a lot going on here. Is it true if you got R equals rho, some constant, L over A? Well, the book's got L, but L is the length of the wire. The length of the wire changes as far as the consideration of what's going on is concerned. At this differential, at a particular length, dx, there's always, you're breaking this wire up here to here. There's a d. That's an L. That's also an L. Yeah, well, that L is really a dx as you're walking left to right. So if you say this, it's a lot like saying R rho, the length of the thing. So you've got this at X length over A, but it's continuously changing resistance. The L and the X, let me see, did I actually say that? I think I said that earlier. No, I didn't. I said it later. I said, the small L equals dx for the previous equation because R is continuously changing. So the equation is valid only for a very short L, dx, continuously accounted for. So you gotta have the dx has to be continuously accounted for. Look, this is kind of in the realm of easier done than said, I guess you could say. If you go dr dx, x starts at 0. This is important. Like I said, this is a mistake I almost made, and we caught it. So that's good that we caught it. This is x equals 0 right here. And all the way to here, this is x equals L. And again, the notation gets used differently in different places. But you start here, and you're moving that way. dr dx is rho over A. dr, a little bit of resistance. Now this is a pretty important thing here, guys. Pretty important thing. It depends on the length. You're adding up differential resistances, and all of these small resistances together are going to give you the total resistance. It's only valid, as it said, the L equals dx for the previous equation. Because capital R is continuously changing because the shape of the wire is continuously changing. So the equation is valid only for a very short L. dx continuously has to be accounted for. And that's what we're trying to say there, you guys. If you do that, what's A? Man, what are we talking about? A has to be continuously accounted for as well. is what has to happen. So even here, you got dr is rho over a, and the a is what? It's the radius. It's pi r squared. That's the r. Pi r squared is all this squared. Let's see here. Let's be careful. How about pi r squared dx? Yeah, it's what it is. I mean, you can write that, and you can write that in numerous ways. Like I said, here's where I stumbled, guys. I just thought it was like we were adding. Yeah, you're adding the negative. R2 minus R1. R2 minus R1 is a negative number. I was going this way and just getting the big drop. What's the big drop? It's the big number minus the small number. That's the drop. Okay, that's the amount of drop. How's that oriented then? Is that up or down? It's down. It's a drop of R1 minus R2, which means you can also make it a negative number. To make it a negative number, you make it R2 minus R1, and that's where we got that. And that's where I was kind of having momentarily some issues with it. Okay, so, and capital L, small l rather, is in here. Let me just make sure it's in there. Okay, there it is. And yeah, it looks good. Looks good. We talk about it, we get it. Look, I mean, I don't know. Here's really what's going on. Maybe this is a little easier to look at. It may be easier to look at, but you can't really solve anything with it because you don't have anything mathematically substantial to talk about regarding what's going on. Here's the pi. This thing right here in bracketed, this thing right here in brackets, squared, right? This thing right here in brackets, squared, you guys, is pi r squared dx. So rho over pi r squared dx. And that's what that was as well. So it's the same thing. Hey, nobody's going to debate this. If this thing started from a point and then went to something big, perhaps this is along the lines of what it'd be looking like if it went from just a point and it was a cone shape or something like that, let's say, but or something close to that or something. But this is a different dynamic. This is what it is. This right here, this generic R, so to speak, being squared. Well, this generic R, this R is the quantity R sub 1 plus the quantity R sub 2 minus R sub 1 over L times X. R1 plus the ratio, the quantity R2 minus R1 over L times X. That's the R. You square it, it's like squaring the R. That's what it is. So this is where it's at. And you want to find out what the total R is. The total R is do an integral from x equals 0 to x equals L, and you're going to be fine. And again, it's a little, so how the whole thing plays out. So you're actually integrating this thing from R equals, whatever it is to, you're actually integrating this thing from x equals 0 to x equals L. Yeah, I know, but you need some substance to what L is, and you got to use that to actually get there. So that's it. And that is about to solve the problem, guys. It is a somewhat odd integral. It's not really an easy integral, but we've got integral tables, And those, how they're able to obtain those answers, there are numerous ways that can be done. And oftentimes they, you can certainly stumble across how to get answers, take some good guesses too for finding antiderivatives. But let's just proceed with this and see where it goes. And if we have to look things up in an integral table, we can do so. Well, we said it has to be done. You're going to have to run from x equals 0 to x equals L. Here goes. The resistance is going to be the integral from 0 to L of what we wrote down. Obviously I just erased it, but we can do it. We got dx here. We got pi. I don't like the way I wrote that, but okay, that's pi's fine. Like pi's like that. The only thing being squared is going to be this, is going to be the radius, and the radius is going to be this rather convoluted looking entity right here. That's squared. And then on the outside you got this. So we've got the rho, we've got the pi. Okay, so it's up here, guys. Let me just, we could take that out of there and deal with it. So the rho and the pi are constants. So let's take the rho and the pi out of there. Correct. Well, now what? Well, try to think different ways you can kind of deal with this. You can take, okay, I showed it a couple ways here. Let me see here. As a note, all right, here's, I guess, where it's going. Just keep your eyes open, guys. I mean, this right here, in our problem, this quantity r sub 2 minus r1, this quantity r sub 2 minus r sub 1 divided by L, that's a constant. That's a variable, and this is a constant. And so I gotta, is there an integral that works? I said, or other people have said as well, I mean, this doesn't lend itself to an easy solution, but we can look it up. You might be able to take a good guess at it and get to it. Most likely, table of integrals is probably the best way to go. This is of the form AU plus B, where A and B are constants. That's as a note, this thing is clearly a positive integral. Why is it a positive integral? Because you're going from 0 to a positive number. And everything down here is getting squared. There's nothing crazy going on here, because even if you put a 0 here, you got B, and B has some kind of substance. Now, who's what? This right here, that right there, the quantity R2 minus R1 over L, that's your A. The X is your U, and the B is the R1. You might want to rewrite it in such a way that it looks like that, but I'm just trying to say this is A, this is U, this is B. This is A, this is U, this is B. The square, the square. The dx, the du. The u is the x. The A is the quantity R2 minus R1 over L. The B is the quantity R1. That's all it is. Well, if you took the, so this is clearly a positive integral. If you were, they kind of just say something here, I guess you could say. Let me try to think here. Right. If you were to take, I mean, it's kind of a guess here. It's more in the table of integrals here. But if you were to take d du, I wrote it different ways in my notes. I don't know. It's kind of a horse apiece. If you were to go d du of -1 over a times AU plus B, getting in the realm of the guesses, I guess, right? Take the derivative with respect to U. Take the derivative with respect to U of this. Wow, what is that? Well, the negative 1 over A comes out. The derivative of this is this quantity to the -2, because it's this quantity to -1 right now if it were up here. The derivative of that would be negative 1 over AU plus B squared times, by the chain rule, times the derivative of AU, of this thing, which is A. Well, wait a minute. A and A cancels. Negative times negative is positive, and you end up getting the quantity AU plus B squared. Wow. The derivative of this is this. What does that mean? That means the derivative of this is that. That means that the antiderivative of that is this. So if you did the integral, this integral comes out to, this guy is the derivative of something. Sure, it's the derivative of an antiderivative. So if you integrated this, you'd get the antiderivative. There's your antiderivative. You would get now again, we just demonstrated a verification more than an actual deciphering of it, more than an actual derivation of it, I guess. But we demonstrated that it actually worked. We demonstrated that it works. There's a lot of times, I bet you much of what they do, they're getting it. They look at these, they take derivatives and say, well, wow, what is that? Well, if you're integrating something like that, with that which I just got, if I integrate something like that, I'll get that thing whose derivative I got. And so there's ways they can compile this stuff. There's brilliant derivations out there. For our purposes right now, we're right here. We got that. Well, what does that mean? That means if you go here, we've got the same thing here. We're just going to say the whole thing that we got to say. I mean, this is our rho over pi. That right there well, we said it was a negative -1 over A. Now, what did we say A was? We said A was this. Which, by the way, is also negative. I mean, Remember, this is the small one. The small radius, the big radius. Small minus big is going to be a negative number. That's negative. Negative divided by negative is positive. Out of the woods that way. That's positive, but still, you're still kind of looking at some negative stuff, but that's all right. It works out. And then you got, again, R2 minus R1 over L times X plus B. B is the R1. Well, don't worry. You're evaluating between two places. This is always the end. The radius by itself is always a positive number. This may not be a positive number because that's a big radius minus a small radius, negative answer. Big radius minus a small radius, negative answer. I get all that. Yeah, I know. But R1 was the biggest of all. And when you do this, this is really just the radius. Every one of these radii, ladies and gentlemen, right here, for example, right here, from here to here, all the radii are going to be positive. This is really just R. This is a negative number. Yeah, it is, because big minus small is negative. Big minus small is negative. Negative divided by a positive number is still negative. Negative divided by negative is positive. Positive times, this is a positive answer. Positive times positive is positive. And this is positive. It's a positive answer. The only thing that would make it go haywire, you guys, are the limits of integration. And even that's not going to be an issue. You go from 0 to L. From 0 to L. X equals 0, so the whole thing here. So let's see what we got. You end up getting, it's the guy I wrote this in about a million different ways, guys. But anyway, you saw what we did right here, guys. Let me get rid of this. It's a lucky guess. I mean, somebody may have been looking at some of these things and saying, well, let's start taking derivatives of some odd-looking functions, and what do we get? Well, we get something that doesn't look very odd. Well, if we do integrate that thing that doesn't look very odd, we can get the antiderivative, which was the function whose derivative we were getting in the first place. And that's probably a lot of the ways that people stumble across this stuff as well, to get antiderivatives. So, I mean, certainly not the only way. There's much more rigorous means of evaluating various integrals. There's the mathematics is nothing short of beautiful, you guys. Deal with it. What do we got here? Well, you can put an L in here, and the L's right here. The L's right here for X. The L's cancel. R2 minus R1 plus R1 is R2. And that's it. I mean, let's see here. Let's do it again. Here you go. You got an L. You got an L for X. Do it between the limits. There's an L for X. Here's the L. L and L cancel. R2, that you got R2 minus R1 plus R1 is R2. R2 times this over L is R2 times the quantity R2 minus R1 over L. The L flips, and we get, let's leave the rho and let's leave the pi alone. R2 times the quantity R2 minus R1 the L flips upward times -1 is negative L minus, put a 0 in here, a 0, huh? Put a 0 right here, you got R1. Put a zero right here, this goes, you just got an R1. You got R1, plus that stuff right there, right? So let's see exactly. Let me just make sure I'm comfortable with this, guys. Yeah, everything does look good. So yeah, it's okay. Put a 0 right there. You got R1. So I don't know. What do you? Well, I can still. I'll tinker with this some more, guys. Let me just write it down as it is. R2 minus R1 over L. Times, for some reason, why the heck am I having an issue here? Okay, no, it's not a problem actually. Let me see here. We had the L in here. The L and the L cancel. You got R2 times that. If you put a 0 here, that's gone. You got R1 times that. What am I'm excessively worried about nothing. So that's R1 times this right here over L. Well, it's R1 so you had, for the first scenario, guys, R2 minus R1 R2 minus R1 for that. Just forgive me, guys. I don't want to do anything too careless here. You got that out of there. That's R2 times the quantity, R2 minus R1. The L comes up. You're good. The other one is R1 times the quantity, R2. R1 times the quantity, R2 minus R1. Yeah, it's just because you put the 0 in here. It's going to be R1 times the quantity, R2 minus R1 over L. The L flips over, and you got negative L here. Correct. Rho over pi. Here's L. This is negative L right here. There's so many ways this is going to go. I don't know how I wrote this at the end, but I'm not even going to worry about it right now. Minus a negative is plus. So we got L over R1, R2 minus R1 minus L over R2 minus R1. What's going on here? Well, R2 minus R1 R2 minus R1 is a negative number. This is a small positive number. So in terms of absolute value, R2 times the quantity R2 minus R1, when compared to R1 times the quantity R2 minus R1, this guy has a smaller absolute value. This has a bigger absolute value. If it has a bigger absolute value, if the bottom right here has a bigger absolute value than that bottom right there, that means this will have a big absolute value. This means it's a small absolute value. It's a small minus number. It's a small negative number. It's a small magnitude negative number. This is a smaller number on the bottom, so it's a bigger value. It's a bigger magnitude negative number. Minus a big magnitude negative number, you get a positive answer. A big positive number. So this will be very negative, is what I'm trying to say, I guess. It's going to be a large magnitude negative number because R2 is small. Everybody's the same, guys. L and the quantity R2 minus R1. L and the quantity R2 minus R1. What differentiates this whole thing? R1 is a bigger number than R2. R2 is small magnitude. This is a small magnitude number. It's a negative number, actually, believe it or not. It's a small magnitude number on the bottom. Small magnitude on the bottom means big magnitude answer, but it's negative. Okay, well the opposite of a negative is just a big positive number. This is going to stay negative, and it's going to be a small negative number in terms of magnitude because R1 is big. So it's a small magnitude negative number. Small magnitude negative number added to a big magnitude positive number. This number right here is plus a negative. That's positive. This is going to have bigger magnitude, and it's going to be positive than this is going to have, and that's negative. That's negative, that's positive, but this has bigger magnitude, so it's a positive answer. It better be, because the resistance is a positive answer. The resistance is a positive answer. So there's ways you can clean that up a little bit and write it as you want. So we're, it's a true story, okay, whatever that means, it's true. Can we maybe make this, okay, what I said is true right now. It's a guaranteed positive answer, period. Tell you what I'm going to do. What do you say I multiply by a special one called let me multiply by a special one called R2 over R2. R2, R2. Let me multiply by a special one here called R1 over R1. And that's the same as putting it here, R2, R1, R1, R2. True. All right, can we talk? Can we make this thing simpler? Okay, we've said a lot. Okay, it's a mess, but we can do it. Roll over pi. You got the L there too, huh? All right. Let's pull the L out of there. And yeah, looking pretty good. This is interesting, fascinating, really. Pull the L out of there. Pull an L out of both of those. I wrote it plus a negative. Plus a negative is the same as just minus a positive. Plus a negative is the same plus regular without putting a negative in front. Pull the L out of there. You got R2 plus a negative R1. R2 plus a negative R1. Right? Look at it. Look how it was. R2 plus a negative R1. R2 plus a negative R1 is R2 minus R1. True, because you worked hard for the common denominator and you got them. R2 minus R1. True. I got more news for you. Is 3 minus 10 negative 7? And is 10 minus 3 positive 7? Look, check it out. If this is 3, because it's a small one, right? 3 and this is 10. 3 minus 10 is negative 7. 10 minus 3 is positive 7. These are always opposite each other. When you do this, negative 1 at the end. See what we got here. Pulled the L out of there, right? Did we? Yeah, we did. There was an L. Oh, there was negative L's. You got L, L, L. Yeah, it's look good. We had said when we had done the integral, you guys, it was a negative. That's true too. It had to be a negative on top. For some reason, I hadn't put a negative there. The integral of that is like a negative out in front. So in all of this, in my notes, watch out, guys. I should have had a negative in front. Remember we said how that whole thing worked out? When you did that integral of the general form, the integral of du over the quantity au plus b, the integral of du over the quantity au plus b squared, that was negative a over a times the quantity au plus b. When we did all that, that was always a negative in front, guys. Forgive me. I mean, I should have been there. That should have been there. That should have stayed there as a negative. Here's a negative here. You've got negative rho L pi negative 1 over R1, R2. Negative times negative, rho L over pi R1, R2. Pretty interesting stuff. Very interesting stuff right there. It's as though you're kind of getting the average of the two. Yeah, it's fascinating. Actually, is really what it is. Look at this. When it comes to this, and again, guys, the reason I had forgotten to put a negative. Now they're on there. They're on there now. But I had forgotten to put a negative on there because remember when we got this du over au plus b, the quantity squared, we've got negative au plus b. This is the big thing, guys. There's a negative right here. And I don't know what I did. Perhaps my notes were off. I probably was just rushing it too much. But there is that negative there, and it had to stay there when you were doing that. There's something very neat that's got to be said about that as we say this now. Yeah, it's clearly a positive integral. But you still, it is clearly a positive integral, but that is definitely negative right here. And that was, for some reason, I just want to make sure. For some reason, there had to be something different here. Let me just think for a second, guys. Yeah, I think there had to be in the end when we're doing this, there was should be in the notes just fine, but very extreme caution on this one. I mean, we got this. Right. This. Yeah, there should have been, I even in my notes, I had not put a negative on there, and then in the end I had. Yeah, there simply should be a negative. It wasn't. So right, there had to be a negative in there, guys. So watch out. I mean, this is fine. When the negative's in there, it comes out fine. What is immensely, which I think is very, very interesting here about how this happens. I think it's very, very interesting on how this happens is we earlier made a remark, and that was R equals rho L over A. Well, first of all, at the end of the day, guys, this is the answer. Just be careful as you're doing a problem like this, but that's the answer. What's pretty fascinating about the whole thing? You had a situation, guys, where just trying to, if I could just for 1 second look at this, guys. I want to make sure that we are all in agreement here. Right, this would have stayed R1. Let me just see something here, guys, really quickly. Let me make sure I didn't do anything I did not want to do here. R1 over R2. That's minus. This is plus. This is R2. Or R2 is bigger than R1. Okay. Well, this is definitely the answer, guys. I just want to, for some reason, I'm looking at what I might have said here. We said that would be a small number, making it a big negative. Yeah, that'd be a problem. Small number here. R2 is small. R2 is small. That would make this a big negative, and this R1 is big is a small positive. That'd be an issue. You'd have to have a negative there to do that. I think it's, yeah, like I said, when I was doing this is where I must have missed it here. But anyway, the procedure should be spot on when we're talking about something like that, guys. I think I might even take a quick look at it right now. But before I do, I just want to say this is the answer. And what's fascinating about this thing being the answer is, isn't it true that R equals rho L over A? R equals rho times L over A. Well, here's rho, here's L. That's the area of an ellipse. The area of an ellipse, if this thing were composed of a cylinder-shaped object with great symmetry, but each cross-sectional area was an ellipse, not a circle, of area pi r1, r2. Remember we said pi AB for the area. I mean, I said that in other places too. Pi AB is the area of an ellipse, pi AB. Here's the A, here's the B. According to the mathematics here, wow, that's pretty fascinating stuff, unexpected as well. You got rho is this, R is this, rho is that. Rho is that, L is that, and pi AB is that. R equals rho L over pi AB. If it was an ellipse with semi-major axis R1 and semi-minor axis R2, yeah, according to this, it works. If it was completely symmetric, like a cylinder, but an elliptical cylinder, with dimensions semi-major axis R1 and semi-major axis R1 and semi-minor axis this coming out, and that right there with that length under consideration, that would be the resistance. According to what they're saying here. That would be the resistance if it was an elliptical type cylinder, like a cylinder type shape, but every cross section is an ellipse with semi-major axis R1 and semi-minor axis R2, and the area of that elliptical cross section, all elliptical cross sections, would be this. That's pretty fascinating. That complicated thing, this relatively complicated thing, has the same resistance as something somewhat similar to look at, or somewhat easier to look at. Have the same resistance according to the mathematics that we're looking at. Pretty fascinating. You're looking at it, guys. I mean, let me just to get it kind of out of our thought process. I think you guys probably aren't worried about it as much as I am right now, but let me just, like, for 1 minute, just kind of confirm that it was going to be going in that direction where you're getting the negatives right here and you're getting that answer right here. They're saying if you did it with all the stuff we have done, yeah, that should have been the way to go. I mean, right off the bat, if they're saying give me the integral of what I was doing here, guys, R equals rho over pi. This is fine so far. Didn't get crazy yet. You got here, you got the dx here. And then you got this, which is the R2 minus R1, negative number, that's for sure, there, over this. That's A, the X is the U, the R1 is that. Match it up, please. It's got to be this. I think we've really emphasized that negative, right? If you do that, this is the A, this is the U, this is the B. You get R2 minus R1. This is the A. This is the U. This is the B. This right here is the A, the X is the U, so the quantity R2 minus R1 over L is the A, the X is the U, the R1 is the B, and the A is, once again, R2 minus R1 over L. That's all that. All of that over a negative 1. All of that over a negative 1. And then you say, I don't want to erase too much of this, but yeah, let's erase it to here at least. Let me leave some of this up here. So you kind of backtrack that the correction was kind of on, at least on the mark, right? You got this right here. Evaluate between 0 and L. Well, how do you do that? And it's going to be rho, and remember now, it's going to be also rho over pi times negative 1 times that. So what do you get? Do the evaluation. Let's go. You got negative 1 times rho over pi, and that's negative rho over pi. Put the L in here and see what happens. Here's the L. L and L cancel. You got R2 minus R1 plus R1. That's R2. R2 times the quantity, R2 minus R1, all of it divided by L. It's underneath, so it flips up, and you get L. Just L on that one. So it's, you put the capital L, you put the small L right here, small L right here, small L cancel. This plus that is just going to be, it's the top plus this is going to be R2. R2 times this is R2 times the quantity R2 minus R1 over L. The L flips up. L's right here. I already took the negative, this negative, and I put it here. And I got that. Put a 0 in here. 0, gone. R1 times the quantity R2 minus R1 over L. The L flips. We've already taken the negative out. The L flips, so it's minus so it's that. So it should be, you got the negative rho over p right there. Let's just make sure, it should be fine as we were doing this thing from the get-go. We were going from 0, r minus 2, r minus 1. I'm sorry, R2 minus r minus 1. Yeah, that'll work. This right here, okay, yeah, that'll work. What ends up happening is you end up getting, the L comes out, you got negative rho L over pi, rho L over pi. So you pull the L out of there, negative rho L over pi. Remember, this becomes on top, you want to get a common denominator, so it's R1 over R1. So it's R1, you multiply by a special, this guy right here, just right here. R1 over R1, you get R1, R2 times the quantity R2 minus R1. The L has already been factored out. The L has been brought to here. Special 1 multiplied just with this fraction, R1 over R1, R1 right here. Special 1 right here is going to be R2 over R2. The L's already out of there. That's R2. And then you got R1, R2, R2 minus R1. Well, wait a minute. R1 minus R2 is the opposite sign. R1 minus R2 is the opposite sign of R2 minus R1. This goes to negative 1. What's negative 1 times negative rho? It's positive rho. So what happens is, what's negative 1? Rho's a positive number, L's a positive number, pi's a positive number. R1 and R2 are positive numbers. The only negative numbers are occurring twice. And if you multiply everybody else is positive. Rho is positive, L is positive, pi is positive. R1, R2, positive. This canceled beautifully. Everything is positive except that there's a negative 1 times rho L, and there's a negative 1 right here. Negative 1 times negative 1 is positive. And at the end of the day, that's out of there. And at the end of the day, you end up getting negative 1 times negative rho L is rho L. It's rho L over, that's it. Negative 1 times negative rho L is, negative 1 times negative rho L is rho L over pi times the quantity. Over the quantity, pi R1, R2. Okay, that was the mistake. That was it. That was the... and there's a lot of ways to write it. I mean, you saw how I wrote it the last time. You can go back. I simply find it fascinating. R1, R2. Yeah, absolutely true. Yeah, and it sure looks like the area of an ellipse. The math doesn't lie, but that's what it is. And the rho's on top, as we said. How we had written it. I wrote it that way. Whole bunch of ways to write it, but man, that just really stands out at you. I almost can't get over that. I'll put it up here, but either way, it just means the same thing. It's assumed that you're looking at it in that manner. The way I've got it, and the key is this, no big deal. You got rho is a constant, pi is a constant, L, R1, R2. It's absolutely the same thing, guys. No matter how you slice it, it's the same thing there. And that happened, like I said, that happened with that thing right there being, that had to be a negative. That was a negative sign. That was a negative sign. That's as simple as that. That had to be a negative sign. And it had to be a negative sign, guys, because that was a negative sign right here. I just failed to put it there, and that could mess you up. We caught it. I caught it in the notes themselves when I was doing it, but when you try to explain this to somebody, either you explaining it to somebody else or I explaining it in your careers later on when you're looking to try to give a presentation, or when I'm trying to give a presentation, or anybody's trying to give a presentation, yeah, you may be able to get it on your own, but it's good to give a coherent explanation of what's going on, if you can. Hopefully that makes some sense, guys. And the fact that it's an equivalent resistance as you would find in the same kind of material, the same length, but rather than being tapered like this, rather than having a taper like this, it's a straight out, no change in cross-sectional area, same length, but the cross-sectional area wouldn't be this kind of a variance. It'd be a constant cross-sectional area of an ellipse. having a semi-major axis as long as R1 and a semi-minor axis as long as R2. Pretty neat stuff. Okay. Good luck to everyone. We'll talk again. Take care.